Hey folks, before we get started, I just want to apologize for the quality of the sound on this video. I'm now working with my usual setup. This video is about net force, and the goals are kind of to learn what net force is, what the two methods of determining net force are, and then to apply it to some situations. So this is like a precursor video to Newton's second law, and while I will give you the Newton's second law equation in this video, I won't go into the equation and its applications in a lot of detail. So we have this idea of net force, and so in physics the word net means sum, and we use the symbol in math for summation, which is the Greek letter sigma, to denote net force and kind of separate it from individual forces. The idea behind net force is that it is a vector sum of all the forces that act on an object at a moment in time, or a system, which is just a collection of objects. We'll focus on single objects now, and then we'll work our way up to systems of two objects later in the unit. Now, vector sums are special. You can't just like add vectors like you would doing arithmetic, adding numbers, because vectors have direction, and so we have to take into account the direction of vectors. Whenever you add vectors, the thing you find, the result of your vector addition, is called the resultant. And so the net force is the resultant that you get when you add all the individual forces acting on an object. There are two methods to find the net force. The first one can be called like the head to tail method. I call it the tip to tail method. And I'm going to teach this by example. So we have four forces that act on an object, and this would be the associated free body diagram for that object. And so the things I want you to notice, I've tried to color code the forces. We'll see how well they show up in the lighting setup that I have for you at home. But you can hopefully clearly see that the arrows are different length. And so a tip to tail addition is essentially a scaled drawing of the vectors in a specific sequence. So if you give someone, I guess you don't really do this anymore, but if you actually gave someone written directions, this used to be something that I think the middle schools would do. If you give someone a set of written instructions on how to get from one place to another, they have to follow it in sequence. And so the tip to tail method presents each of the forces in sequence. You can add them in any sequence you want. You'll get the same answer, but it asks you to kind of almost treat it like you're drawing steps that you would take on a map. And so that's what I'm going to do here. So I have four forces. I've numbered them in the order I plan on adding them together. And so the way that this works is to start the tip to tail method, you like pick a location in space. Now I see that the like right and up arrows are the longest, so I'm going to start mine here so that I can clearly see, like I have plenty of space up here. And so I'm going to draw my first vector. I take the tail of my arrow, and it starts at my origin, and then I draw all the way to the arrowhead or the tip. And so my first vector is here. If you're doing this method, you can you'll label the vectors, but you'll kind of be able to plan out how you label them, like where near the arrow you label them. So that's the first vector. And the reason it's called tip to tail method is at the tip of the first vector, I begin the tail of the next vector. So F2 is up next. It's 3 newtons to the east. So I start at the end of my first vector, and I go what I believe to be 3 newtons to the east. And so that represents the second force. And then I keep going. So at the tip to the second vector, I start the tail of the third vector. So here's F3, and so that is F3. Now the thing to keep in mind is that these forces happen all at the same time, but this way of adding them arranges them so that this is the way that vectors are added. So this is not actually a sequence. Everything happens all together, but the resultant is going to clue us into what is about to happen to this object. The last vector is F4, and that goes 1 Newton to the west. Okay, so now I have my 4 vectors have been added, and so the resultant vector is going to be, if I start at my origin, I'm going to now draw a 5th arrow, and that arrow is going to go from the origin to the tip of the final vector, and I'm going to essentially like close this drawing, and so this is going to represent the net force. And so the resultant, if I added all 4 of these vectors together, or if these 4 forces acted on this object at one moment in time, the resultant would be this vector. It's pointed in the northeast direction, and it's, I don't know, maybe like 2-ish newtons large, because it's it looks like the same length as F1, but it's probably a little bit different. This method is something that we're not going to use explicitly to solve problems mathematically, but it's something that can be very helpful to solve problems visually. If you, basically if you enjoy geometry, this could be good for you. And so that's the first method. There's no mathematical result here unless you actually draw this to scale. In other words, if you made every newton equal to a centimeter and you got out a ruler and measured these, you would actually be able to measure the length of this arrow and convert it very easily to newtons. And if you drew them to scale, you could even get out a protractor and you could find out the angle at which this vector points above that horizontal. So that's kind of the first part of that. Okay, and so unfortunately this video is a pretty long video, so we're going to move on to the other method, which takes a little bit more time but yields very accurate results. So the second method is called the component method, or adding things based on their components. And so we're going to use the same 4 vectors that we just did and add them by component method. Now by component method I mean mathematically, not visually. So we're going to use our understanding of vectors to do some vector math. And in our second example, we're going to work with trig the whole time. In this first example, we'll just work with trig a little bit. So it's the same free body diagram, but I have this this method that is going to be really important for us. I have vectors that point in all 4 cardinal directions. Now, in our projectiles unit, we spent a lot of time talking about how the x direction operated separately from the y direction. And I mean, that's not really true because things happen in 2 dimensions all at once, but mathematically it makes more sense in physics to break things down into their x and y components and work with them mathematically there. So we have like 2, instead of talking about the overall net force, we're going to talk about the net force in the x direction and the the net force in the y direction. So we do this to kind of like with the same philosophy as we did in projectiles, that it is makes mathematical sense to add things up in the horizontal direction separately from the vertical direction. And the reason we do this is because we can actually do arithmetic with them, but we have to be very careful. So the way this works is, if we imagine north, south, east, and west as like the directions of the x and y axis, we can assign these vectors positive and negative values in their respective direction. So in other words, the north direction is positive while the south direction is negative. The east direction is positive and the west direction is negative. And this is basically, if you like slapped some cardinal directions on a coordinate plane, you'd get the positive x-axis was pointed east and the positive y-axis was pointed north. So we go with those conventions in physics. That means that the net force in the x direction is going to be the sum of the right pointing forces minus the sum of the left pointing forces. I put this summation notation because sometimes there's like more than one force acting to the east. So you would add them together first. For the y direction, it would be the sum of the up forces minus the sum of the down forces. And so I hope to show you exactly how this works, and then close it out with the trig. So the net force in the x direction is the right force minus the left force. And so we have 3 newtons to the east, so I go 3 newtons that's all of the forces that point to the right, minus and then the west force is 1 newton to the west, and so my x net force is 2 newtons. And that is a positive number, so I don't actually need to like specify east or west, because my convention for finding the net force does that for me. In the y direction, I have the same deal. My positive force is the up force, that's 2 newtons. My negative force is the south force, that's 1 newton. And so the result of that is a positive 1. So 1 newton. And so far you haven't really seen like components yet, but we're using the forces are all on an axis, and so I don't need to do any trig because they're already horizontal and vertical. So I get the following understanding. I can now draw a triangle, and I can say, okay, well, I can go 2 newtons this way, and that is the net force in the x direction. I can go 1 newton this way, and that is the net force in the y direction. And so my net force is this arrow at this angle. So that is the overall net force. So obviously if the 4 forces push on this object at the same time, it is going to be pushed to the right and up, in other words to the east and north at the same time. And so I need to like incorporate that into my my math here. So to find the net force, I do 2 things. I can do Pythagorean theorem, and I can say the net force equals the square root of the net force in the x direction squared plus the net force in the y direction squared. And so that is essentially the square root of 2 squared plus 1 squared. And that is equal to 2.2 newtons. So it's a little bit larger than the north force. And the last thing I can do is find the angle. And I can use any trig function I want, but I'm going to use tangent. And it's going to be the net force in the y divided by the net force in the x. And so that's going to be the inverse tangent of 1 over 2. And so that's 27 degrees. I'll just round that to a whole number. So when I report that net force, I have to keep in mind how I drew my triangle and also these numbers that I have. So the net force is 2.2 newtons at 27 degrees. And then you can kind of be like simple, or you can be fancy. You can say 27 degrees above the positive x-axis, or you can say something like north of east, meaning your overall vector is pointed to the east, and that angle is drawn north of the east direction. And so this would be your answer for net force. Okay, I'm gonna stop there and make a second video because this one's getting pretty lengthy. So I'm gonna recommend that you stop here, take a little break, and watch the second video.